Well, hello everybody, Dave here, and today we're going to start a series of lessons on exploring data. And one of the big things about statistics is understanding what kind of data you have, because there's different tools depending upon the data that you have. And it's important to use the right tools for the right data so that we can make meaningful conclusions that allow us to, more importantly, make meaningful analysis of that data once we've performed them. So it's going to be really important throughout this series of lessons to understand the type of data, why we know what the type of data is, and most importantly, what kind of tools do we have to be able to analyze it. So the first question I like to ask my classes is, what have you even signed up for? Because a lot of people understand that statistics involves math, but they don't necessarily know what we use the math for. And in short, I like to describe it as advanced data analysis. It's taking raw data and being able to organize it and create visuals and perform calculations such that we can begin to understand what the data represents and, more importantly, what conclusions we can make based upon that representation. So it is a powerful tool used in many disciplines from business to science. And so it's important to recognize the fact that this is a very universally used mathematical skill. Now, one of the first things we have to understand about the data, of course, is what's involved. And typically there's two things that come out of any data set, and it's individuals and variables. And so when we speak of individuals, we might be talking about something like NBA teams, where the individuals would be all of the actual names of the NBA teams, where a variable of interest is a specific characteristic of those teams. So maybe it's the win percentage, maybe it's the points per game. And so when you have the understanding of individuals and variables, we can then split it up into the only two types of variables that you're going to deal with in statistics, and that's categorical variables and quantitative variables. And one of the most important skills early on in your statistics career is understanding the difference between the two. Because with categorical variables, you're going to see individuals and you're going to see categories and you're going to see quantities in categorical variables, and you're going to want to understand why you can't do certain calculations like you can with quantitative variables. And the key thing about quantitative variables is to understand that if the numbers make sense to take the average of, that's a quantitative variable. Take an example like jersey numbers. If you take the average jersey number of a team, that number is meaningless. There's no reason why you would want to take the average of a jersey number. It's great that you can do the arithmetic, but if the arithmetic is used for no reason, then it's a nonsensical idea here in statistics. With quantitative variables, if we're talking about the average weight of something, well, even in the way that I described it, the average weight of something, it makes sense to take weights and add them up and divide by the total and get that value. So whenever you go through your data sets, you very first want to take a look and understand, are we dealing with categorical variables or are we dealing with quantitative variables? Because all of the tools that you're going to learn over the time in this course will involve understanding that idea first. So if we key on this idea of variable, let's say that we have a table like this with a different set of models of cars and their respective miles per gallon. Well, if we take a look then, the miles per gallon is what we would consider to be our variable of interest, where the individuals would be the type of car that we're talking about. Well, if we create a plot of this, what we end up with is something known as a distribution, which is essentially what values the variable took and how often it actually takes it. I also like to describe a distribution as understanding a little bit about the actual shape of the data itself. You can see with this plot at the bottom here, which is known as a dot plot, what we've done is we've put a dot every time that value occurred in the data table. So you can see that at 14 miles per gallon, there is one data point, whereas at 26 miles per gallon, there's two data points. This dot plot is something that we're going to talk about a lot in the future of this course, and it is a quick and easy way to instantly get a sense for the distribution of your data set and perhaps some other ideas about the data set that we may not be able to see from the table alone, like are there any values that are really far away from the standard distribution, and perhaps is there any sort of description of the shape that we can make that can maybe make more sense of the data set as a whole. So stay tuned for more on dot plots, but it is certainly a very nice way to take a look at the distribution of a data set. So if we were to explore this data set a little further, the first thing I'd want to do is take a look at the individual variables and understand the relationships among them. For example, if I notice miles per gallon, maybe there's a relationship between the luxury vehicles and their resulting miles per gallon. Or perhaps there's cars in here that are considered hybrid vehicles. Or perhaps there's some number that really sticks out to me that makes me question, I wonder what's going on with that particular pair of car with its miles per gallon. But on its own, a data table is not going to be good enough. So you always want to start by taking a look at a graph to try and understand things a little more. So now you can see that we have a Rolls Royce and we have the Bentley, and those are the ones that are on the far left of this particular plot. Well, that's interesting to me because if you take a look at something like the Toyota Camry, that's more in line with the rest of the distribution. And so from the plot alone, you can begin to start to make these statements. You're going to be able to make calculations later on that are going to help you justify statements that you make. So if we take a look here, this is a window from a TI calculator, and it is one of the most important tools you're going to use early on because all of the statistical tools that we're going to talk about from a calculation perspective are actually built into those TI calculators. Now, if you have a Casio or some other type of calculator, those are great too. But I'm going to focus in on the calculators that I'm most comfortable with, and that's going to be the TI system. One of the beautiful things about the textbook that I use, which is the Darren Starnes Practice of Statistics book, is that they have a technology corner that they actually explain for you how to use that calculator more effectively. I am sure that other textbooks do the same thing, but I certainly like the layout of this particular book. So I would encourage you to Google your particular calculator to help you understand a little better how to use that. But if we take a look at that window, one of the first numbers I see is the very top number, which is X bar. And that's actually representative of the average. And so what we found out from a simple one variable statistic is that the average of this data set is 27. And if we take a look at the plot, we can see where 27 is, and that's basically in the middle of that one clump, absent of those luxury cars that we've already talked about as being interesting that they're so far away. So even with just a simple data set and a simple plot and a basic calculation, you can begin to understand the power of statistics and why it is exceptionally useful in helping us understand more what data is all about. So one of the most important aspects of statistics is the ability to actually get the data that we're going to analyze and what we're going to do from the point of creating the study all the way to the end of the study when we actually start to make inferences or conclusions of what that data actually means. So all data analysis starts with a population of interest. And from that population, we have to decide what sample we're going to take from that population. We're going to collect that data in such a way that we're going to be able to perform the data analysis, such as creating the plots, making calculations, and things like that. These first couple of steps, especially the identifying the sample, identifying the method by which you're going to sample, and then the analysis you're going to perform, this is exceptionally challenging for anybody who's creating a study, because finding a way to sample a population so that it is representative of the population of interest is exceptionally challenging. And you will find that as we go through this course, I will constantly refer back to this particular diagram to represent the idea that we are at the point now where we are determining what the sample is, or we are doing the analysis, or we are doing the most important part of any sort of data analysis, making inferences about the population. And once we understand this entire cycle, we can begin to understand how to fill in the blanks of what it means to sample, what it means to analyze, what it means to make an inference. One of the most important aspects of any sort of statistical study is that we can take our values and be able to extend it to the population as a whole. Because in a lot of cases, we're not going to be able to do so. We're only going to be able to describe the group that we have studied on its own and have not produced a data set allowing us to make some sort of inference about the population. So the grandiose idea of statistics is to go along this cycle so that once we make an inference about the population, perhaps we do a new study of the population to find something else out. Or perhaps we find a different population and perform the same study to see if there's any difference between the populations. And so data analysis and statistics is an exceptionally powerful tool that allows us to take a small group and have them represent a large population, and to do so within a certain level of confidence or significance, which is just an amazing feat when you see it in action. So let's talk about that first type of variable that we referred to, which is a categorical variable. And what you see below here are two tables. One is representing the frequency of the number of radio stations in the United States. And you can see that we have the variable, which is the format of the music for the radio station. The value of that format now would be the type of music, and the count of those radio stations is just considered to be the count. And so if we take a look at something like adult contemporary, we can see that there's 1,556 of them in the total of 13,838 radio stations. So if we did that as a fraction, if we did 1556 divided by 13,838, what we would get is 11.2, or the relative frequency of the adult contemporary radio stations. And so with categorical variables, what we often do is take these data tables and either deal with them in terms of count alone or change them into relative frequencies and then represent them using a different type of visual aid. So these are essentially the two classic examples of categorical variables and the way that they're represented in a table. Now, when it comes to this type of data, there's really only two ways to represent it visually. And the first one is this idea of a bar graph. And so if we take the actual counts and we put them in a bar graph, all of you at some point in your educational lives have made a bar graph before. And you can see at the bottom here that we have the type of radio station on the bottom. And then on the vertical axis, we have the actual count itself. And one of the important skills to have is going to be the ability to glean from this graph things like which one happens the most, what is the actual number of radio stations that are adult standards, and be able to actually take the scales and read them appropriately. Now, one of the common mistakes about a bar graph is the belief that the bars have a position that matters. And if we take a look at a bar graph, we can see that I have no rhyme nor reason to where I put these other than alphabetically. But I could very easily take country music and put it at the end of the graph, or I could take Spanish music and put it in the middle, because there's nothing that requires it to be in a certain position on the horizontal axis. So one of the things you want to always avoid when it comes to a bar graph is trying to make sense of the shape of it, because the shape is all relative to where you actually put the bars. And I could very easily make this look like a clumped graph, I could make it look like a symmetric graph, or I could make it look like it's a random graph, just based upon where I put the bars. So be very wary about how you read a bar graph. So if we take a look at the relative frequency table now, there's two things I want to point out. The first thing is that we don't have a sense of scale of the study itself. Just because we have the percentages, we don't actually know how many radio stations in total have been observed. And so when we see a percentage like 6.3%, that could be 6.3% when we had 1,000 radio stations, 5,000 radio stations, or 10,000 radio stations. We just don't know. All we know is that there are more country stations relatively to rock stations and to Spanish language stations, but we don't actually know by what count. The other thing I want you to notice is at the bottom of this table, the total percentage only adds up to 99.9. This seems weird because it would make sense that the percentages all add up to 100%. Well, what we've done is we've rounded all of these percentages to a tenth, which means that at some point we probably lost this tenth of a percent somewhere. And so don't be shocked that we ended up with a relative frequency table with a total of 99.9. If you end up with something like 92.9, you've probably made a calculation error. The best way to represent this type of data is typically a pie chart. And I don't want you to think about your grade 8 days where you had to take out a compass and you had to take out a protractor and you had to make everything nice and perfect and measure the angles and calculate them and things like that. In AP statistics, all we're looking for is the ability to understand what pie charts mean and, more importantly, create the slices in such a way that they are relatively the right size. The 5% slice is a little larger than the 4% slice. The 8% slice is a little smaller than the 11% slice, and so on and so forth. One of the key things about a pie chart, of course, is the legend itself. And it's going to be really difficult with pencils alone to create a pie chart that has this many different categories to consider. But typically you're not going to deal with anything that has more than about 6 or 7. I would not stress about the actual mechanics of creating a pie chart, but I would certainly understand what they represent. Notice again, the percentages are actually written in the slices just to help us along, and the color scheme is a nice way to know exactly what that slice means. So there are some things to be wary about when you're looking at graphs. The first thing is to recognize if the bar graphs have exactly the same with bars. Because what some people will do to try to mislead you towards a conclusion is they will make certain bars larger than others to add importance to them. When we create graphs in statistics, all we want to do is create a graph that speaks for itself. So all the bars should be the exact same width. When we're dealing with other types of graphs, you have to watch out for some classic things that people try to do to mislead you. When we're talking about pictographs, which is taking pictures of stuff to represent those objects, what typically happens is they change the sizes of the objects to add importance to them. So if we were taking a look at the different types of balls used in games, you might see a basketball and a baseball and a tennis ball, and in resizing them in such a way, you might be able to be misleading in the count by doing something like make the tennis ball bigger or make the basketball smaller, so that the actual horizontal or vertical height is representative of the wrong conclusion to make because you've just made the picture so large as to make that particular column a little larger. The other thing to watch out for is playing around with the scale of a graph itself. If you look at the vertical scale, almost all graphs should start from 0. And the reason for that is we don't want to be misleading in the difference between the bars. So if we have something that's between 0 and 100, and there's only a difference of 1 or 2, those bars are going to look essentially the same height. But if now you change that scale and you shrink it down so that maybe it only represents a value of 5, then that difference in the bars of 1 or 2 is going to be far more dramatic in the way that it looks. And what you will do is make an improper conclusion that, oh, that value must be significantly higher than the other, and what we end up with is another misleading graph. This is very typically done in any sort of political forum because they want to drive you towards particular conclusions about who is winning or what the opinion is. And so be very wary of the way that graphs are represented, and always take a look at the scales, always take a look at the relative sizes of things. When you have two different variables to consider, what we end up with usually is a two-way table. And so what we have are two categorical variables. In this case, we have gender, and we have the opinion of our chances of getting rich. And when you take a look at this table, the first thing I want you to recognize is that in bold, we have the totals. These are typically not given on a two-way table, and one of the first things I encourage you to do anytime you see a two-way table is actually take a total across the rows and down the columns. And if you've done that properly, that number in the bottom right corner should be the sum of the values of the female column and the male column, and it should also be the sum of the values of all of the different chances of getting rich. If those don't add up, then there's something wrong with your arithmetic somewhere. Go ahead and make the change. But one of the key features about a two-way table is the literal ability to read it in two different ways. I can read down the column of females and talk about their ideas of the chances of getting rich. Or I can read across the rows and understand the difference between males and females and their belief that there is no chance at getting rich or a good chance of getting rich. And when you start to take these two-way tables and make these statements, what you start to do is begin to glean from it some potentially meaningful conclusions about the relationship between gender and your ideas, in this case, of getting rich. So two-way tables are a very powerful tool, and they come up a lot in statistics. So you want to make sure that you understand the next statements that we're going to make. So now that we understand how to read two-way tables, we can begin to extract some useful information from it. And the first thing that we're going to create is a marginal distribution. And one of the key things about a marginal distribution, first and foremost, is that you're actually going to create a new table based upon calculations. And the way it works is we're going to hold one of the categorical variables constant and then take the sum of all the individual counts within that particular category. When we do so, it's going to be important that we always make the calculations in terms of percentage instead of counts, because we're trying now to compare values across different groups, which means that the relative frequencies are going to be far more useful to us than the actual counts themselves. So in general, to examine a marginal distribution, once you do all the calculations and create that table, and it's going to be a very important thing that you do this table first, you can then create a graph which can display the marginal distribution and perhaps give us some more information that we didn't see from the numbers alone. So let's say we want to create a marginal distribution for the chances of getting rich. The first thing we want to do is create a new table where we have all the possible responses to this survey, which is either almost no chance all the way up to almost certain. And then we want to take the totals across the rows. we're going to take that total and divide it by the total number of people in the study alone, and what that's going to give us is the percentage itself. We do that for each of these responses, and what we end up with now is something that should add up to 99.9 or 100%. Well, what we've done now is we've created these relative frequencies within this table alone, and we can see that 4% of people thought that there was almost no chance, or 29.3% thought that there was 50-50 chance. And you could maybe get similar information just by reading the two-way table alone, but now that we've created this marginal distribution, it makes it a little more straightforward to actually physically see the relationships between the answers and the number of people that actually answered that particular response. If we create a bar graph to help us with this, the only difference between this bar graph and other bar graphs is that we have the percentage on the vertical. And we can see here that people are generally optimistic of their chances of getting wealthy. There is clearly a higher percentage of people that said 50-50 and above than there is that said almost none and some chance. And so this marginal distribution that we've created can be very useful if we want to start trying to make some inferences about people's opinions of our chances of getting rich. But let's say that we want to know something more about the relationship between gender and these answers. If we have the condition that given that someone is female, what were their answers, versus given that someone is male, what are their answers, this is referring to something known as a conditional distribution. And it's basically holding one of the variables constant and then determining the relative percentages based upon that variable. And so when we actually examine or compare conditional distributions, the first thing we want to do is determine which row or column we're interested in. Is it female, is it male, or is it perhaps one of the answers? Then we're going to use the data in the table and we're going to calculate the percentages based upon that variable. And once we do so, a graph of either a side-by-side bar graph or a segmented bar graph, which we'll show you shortly, can be used to actually determine if there is some sort of meaningful conclusion we can make about these variables once we have it. So you'll notice that even with another distribution, we're still trying to create a visual to help us understand if there is some sort of conclusion we can make. So always remember with raw data, this is pretty much our ultimate goal, is to try and get to a point where we can see something that perhaps helps us with a conclusion. So let's say we want to create a conditional distribution of the opinion among males. Well, the first thing we have to do again is recognize the fact that we're only going to focus on males now. So we have all the possible responses, but this time when we calculate the percentages, you'll notice that we are only taking the male totals. And most importantly, if we look at what we're dividing the values by, we're dividing it by the total of the column itself. So that column of males is what the column of interest was. We could do the exact same thing for females. And notice again that when we calculate the percentages, we're taking the total of people who are female that said there's almost no chance at getting rich, divided by the total of all females in the study. So in this case, we're not using the total number of people in the study. We're only using the total of the specific category that we are actually interested in. Now, when we do that, we could create what's known as a segmented bar graph. And a segmented bar graph is very easy to spot because what you see are one or two bars with these different levels. And one of the key thing about these levels is that they all add up to 100%. So what we've done is we've essentially taken our calculated values from our conditional distribution and we've stacked them one on top of each other, and we've done the exact same thing both for males and females for the sake of comparison. And what we can see just by looking at this segmented bar graph is that generally the same proportion of people who are males and thought there's no chance is about the same for females. But if you take a look at some chance, you can see that there was a higher proportion of females that thought so, as opposed to the idea of almost certainty in getting rich, where it is clear that a larger proportion of males thought that it is almost certain that we're going to get rich. So all of a sudden, we have a graph that allows us to start making comparisons across the genders. And this is the power of a conditional distribution, is we are no longer just looking at the total, regardless of if you're males and females. We are looking at specifically if you are male, if you are female, and then being able to compare across the bars. So a segmented bar graph is something that absolutely you're going to need to know how to create a conditional distribution, and then the actual graph itself with the appropriate scale up to 100%, and a legend that tells you exactly what those segments represent themselves. It is a powerful tool, that you absolutely are going to need to work on being able to create. So the last thing I want to say about categorical variables and dealing with these segmented bar graphs and trying to come up with relationships is I want you to be very careful with how concrete you are about the language that you use. One of the things that you're going to have to get used to with statistics is it's not concrete language like you would have in a regular math class. 1 plus 1 is definitely equal to 2. But in statistics, 1 plus 1 is about 2. It's around 2. It's potentially 2. All of a sudden, you're going to go from this very yes and no to the nice shade of gray, maybe, perhaps. And so when we're talking about associations in the case of a segmented bar graph, do not say that it is absolute. Say that there is evidence to suggest that perhaps there are relationships between gender and your overall feeling of whether you're going to get rich. But at the same time, we don't know about any outside influences that may be affecting these responses. Maybe these folks come from a very affluent neighborhood. Maybe these folks come from a neighborhood to where perhaps poverty or perhaps they're middle income. Who knows what the situation is of these people that are being surveyed? For all we know, if we go to a different part of the world where maybe lots of people are rich, maybe these particular segments would change. And so it's always important that when we're taking a look at categorical variables, when we're taking a look at graphs like this, that we take any conclusions we make with a grain of salt, because without more information about the background variables at play, there is no telling whether these results could change. So that's it for this lesson. I would encourage you strongly to go now and start practicing creating these segmented bar graphs. I would definitely do the calculations for a marginal distribution and a conditional distribution, and I would make sure that you start to understand pretty clearly what the difference is between categorical variables and quantitative variables and what we can actually do once we understand a two-way table. Best of luck to you, and we'll see you again.